So today I want to talk about an object on the moduli space of stable bundles, which is equally natural as the integrable system, but raises the sort of questions that Andrei just said, like what is really going on? Because what I'm going to do is to give you, set up this odd integrable system, give you some examples, and then plenty of conjectures, and hopefully some of you might get interested in it. So let's go back to the usual situation, that the ordinary or commutative integrable system. So I'm formulating now in terms of principal bundles to begin with. So in the original situation, we have a Higgs field with values in the algebra of a semi-simple group, let's say a simple group. Then we have a basis for the ring of invariant polynomials, P1 up to Pk, and these have degrees, 2 for the killing form, and then D3 certain degrees. And when we evaluate the polynomial Pi on the Higgs field, then we get a holomorphic section of the dith power of the canonical bundle. So then, if we take f in the dual space of that, we get a function on the moduli space of Higgs bundles. And the feature is that M is a symplectic manifold, and F1 and F2, they Poisson commute. So this gives the structure of an integrable system, which we've been seeing in many lectures so far. There's another way of looking at this. If we restrict to the cotangent bundle of the moduli space of stable bundles, which sits as a dense open subset, then there's a C star action along the fibers, and each Pi is, of course, homogeneous at degree Di. So instead of thinking of a homogeneous function on the cotangent bundle, we can think of a symmetric tensor on the bundle stable moduli space of stable bundles. Symmetric tensor, a section of the Di symmetric power of the tangent bundle. And then we have to understand the Poisson bracket of two functions on the cotangent bundle as being the Schouten bracket, a certain bracket which generalizes the Lie bracket of vector fields on sections of symmetric powers of the tangent bundle. So we take a bracket, the bracket of something which is in the mth symmetric power and in the nth symmetric power, then it goes into m plus n minus 1. So now the odd system comes from looking at skew symmetric form. So we have a basis for the algebra of invariant forms on a Lie group. And there are generators corresponding to each generator of the symmetric polynomials. So these have degrees 2di minus 1. So for example, the killing form of degree 2 gives us the canonical 3 form on a simple Lie group. And you can do the same thing. So you take now an invariant form, evaluate it on phi 1 up to phi whatever the degree is, and that will give us a section, a holomorphic section of power of the canonical bundle. And then we take something in the dual space of that. What we get is a holomorphic section of this power of the tangent bundle, which these are called polyvector fields. And there's a bracket on these as well. It's a similar kind of structure that we have a bracket operation which generalizes the Lie bracket and ends up from the mth exterior power and the nth exterior power into m plus n minus 1. And the fact, okay, this is a fact that these sections commute according to this Schouten bracket. So that fact comes from an infinite dimensional quotient construction, just as the integrable system does. On the other hand, we know that there are other ways using algebraic geometry of proving the Poisson commuting of those functions in the integrable system. For example, actually, if you look at Beauville, Narasimhan, and Ramanujan, there's an argument in their paper about finite dimensional argument about the integrable system. In this case, I don't know of any algebraic geometric way of proving that these things commute. So if any of you want to take up that task, then that will be certainly very good. So, so the basic example, which most of the time I'll be talking about this, is the one that corresponds to the Killing form. So it's basically the alternating one is this. We take the Lie bracket and then evaluate on a third element using the Killing form. So typically, if we take a triple of Higgs fields, then trace phi 1, phi 2, phi 3. That's the evaluation of. So we think of phi 1, phi 2, phi 3 as being 3 cotangent vectors, and we apply this invariant alternating form to that, and we get a section of the third exterior power of the tangent bundle. And so I wrote about this in a paper which appeared in this volume several years ago. And I've been returning to it off and on ever since. So this is an opportunity to try and get other people interested. And so here's another way of looking at both the symmetric and the skew symmetric one, at least it's easier in this low degree case. So we have an element of H1 of the dual of the canonical bundle. You evaluate that on a Higgs field, and that gives you something in H1 of the adjoint bundle, which is the tangent bundle. That's the usual symmetric form. The alternating tensor is that we take something in k to the minus 2. We take the bracket of two Higgs fields. That ends up in add p tensor k squared. We evaluate on that, and we get something in the tangent bundle. So that's a bilinear form with values in the tangent bundle. So it's a skew form altogether. And so, yeah, so as I say, I've been looking at this off and on over the years and trying to persuade other people that it's interesting. And I kind of, you know, so here, this is from Google Scholar, okay? So you see the citations for the usual integrable system. And now you see the citations for this paper here, 6, right? And I'll tell you that three of them are not actually about polyvector fields. They're about a conjecture I made about Lie algebras, actually. And one of the citations is a paper I wrote myself. But actually, while we're about it, and since there are people in the audience who like three-dimensional subgroups, let me just say what the Lie algebra conjecture is, because if you don't, like most people, if you don't like polyvector fields, you might like this one. So let's go back to, okay, let's go back to this. So you see these, we have this basis of invariant forms on a Lie algebra. And they have these particular degrees, right? D1 up to dk. K is the rank of the group. So if you have, if you look at the principal three-dimensional subgroup, so that's a copy of SU2 or SO3 inside the group, and you decompose the Lie algebra according to the three-dimensional subgroup, then what you get are irreducible representations of SU2, which have exactly those dimensions. So the obvious thing to do is to take one of these forms, these invariant forms, and restrict it to the subspace, which has the same dimension, which corresponds to it. And the conjecture is that that restriction is non-zero. So it's obviously true for the three form, because that's the basic three form, invariant three form under the algebra. And the three-dimensional representation is the Lie algebra of the SU2. So that becomes some multiple of the standard three form on SU2. The others, well, there are one or two what we know about. So I leave that as a problem in Lie algebra theory, but I hope that in the future there might be more citations relevant to the topic I'm going to be talking about today. Okay, so the way I want to start is with examples. And the examples actually reveal, or possibly reveal, some feature about this. And this is that, as we know with the usual integral system, that when we take a Higgs field, then if you like, it lies in the adjoint representation, which means that if I take the vector bundle and tensor by a line bundle of order n, if n is the rank of the bundle, that leaves the Higgs field unchanged. And so when we evaluate a polyvector field, then we're going to get something which is invariant by the action of this group. In general, it comes from a Heisenberg, kind of Heisenberg. But anyway, it's just the abelian group of values Zn. So that's a criterion which we can use to kind of look for where these trivectors are. And so the place to start is, of course, one of the first examples of, you take the curve C of genus 2 and look at rank 2 bundles with trivial determinant. Then the moduli space of semi-stable bundles is P3. And then, of course, this is a three-dimensional manifold. So trivectors, polyvector fields of degree 3 are just sections of the anti-canonical bundle, which is sections of O4. So they're given by quartics. On the other hand, if we look at, so we're going to evaluate this three form, this three tensor, if you like, on phi 1, phi 2, phi 3, and this is going to be a cubic differential on C. So in general, there are 5G minus 5 cubic differentials. And so for the hyperelliptic curve, genus 2, then they're all of this form. This is the 5-dimensional space. But what we know is that the hyperelliptic involution on the curve C acts trivially on the moduli space. And so what we need to get is a cubic differential, which is invariant under y goes to minus y. So, okay, on the one hand, this shows that actually in low genus, at least in genus 2, there's this map from the dual space of cubic differentials into the space of polyvector fields is actually, it's not injective. And then in fact, it lands up in a one-dimensional space. So that suggests, or that tells you that this is a distinguished quartic surface in P3, but there's no prizes for guessing what it is, because the semi-stable locus is this Kummer surface, quartic surface of bundles which are S equivalent to a direct sum, degree 0 line bundles. And you can kind of check, well, this is just a check. So it's L plus L dual actually has a 4-dimensional space of Higgs fields. So and this is, of course, set in the this is in the semi-stable locus. But if you look at if you represent a point there by a non-trivial extension of degree 0 bundles, then you'll see that actually you have a 3-dimensional space of Higgs fields, but the Higgs fields all fix the subbundle L, which means that they lie in a 2-dimensional, at each point in a 2-dimensional subalgebra of SL2, and so the invariant 3 form vanishes on that. Okay, so we move on now. So these are all the, I've been looking at all the individual cases which have been established over the years. So these go back many years to the work of Ramanujan and Narasimhan and Seshadri. So now we have the famous intersection of two quadrics. And in this case, we have, okay, so, well, I think I gave you not a formula, I gave you an equation, an expression for the Higgs fields for this. We'll meet it again later on, where it was expressed essentially as a parabolic bundle on P1, that by reduction, by invariance under the tensoring by the line bundle and invariance under the hyperelliptic involution, we get down to something which is on P1, which means that evaluating this triple of Higgs fields gives us something which is a polynomial in Z. So in this case, we lie inside the, if you like, the anti-invariant part of the the quadratic differentials. And so we should get a four-dimensional space of trivectors. So saying this again, so in this case, the anti-canonical bundle is O2. So that means we should be looking at quadrics, but if we impose the invariance condition, then we're looking at quadrics this type. So that's a six-dimensional space, except modulo the two quadrics which define the intersection, that gives us a four-dimensional space. So our four-dimensional space of sections of the third exterior pair of the tangent bundle, in this case, are evident from this and correspond to those cubic differentials. Of course, the fact that these things commute under this Schouten bracket is trivial in this case because this is the top degree. But we can move on a bit. And so in this case, if we look at curve of genus 3 and look at rank 2 bundles with trivial determinant, then the moduli space is a special quartic hypersurface inside P7, so that's six-dimensional. And so if we can identify these 5G minus 5, so that's 15 minus 5, we're looking for a 10-dimensional space of trivector fields on this quartic. And because it's six-dimensional, then the bracket of two trivector fields lies in the fifth exterior power. So this is a place where commutativity should appear. Not that we can see it directly, but we can apply the invariance just to see if there are the right number of trivector fields. And so there's a couple of exact sequences here. One is you restrict the tangent bundle of the projective space to the quartic, and then we have and that gives us a homomorphism from this fourth exterior power to the one that we're after. And then we have the standard sequence on projective space, which will tell us that what we're looking at here, which appears in that exact sequence, comes from the fourth exterior power of C8, the underlying vector space for the seven-dimensional projective space. And so from the exact sequence, you see that the holomorphic sections of this on projective space are isomorphic to this fourth exterior power. So now you can look at the invariance, and you can calculate the invariant part of that fourth exterior power. Of course, the fourth exterior power is very big, but the invariant part is seven-dimensional. So that way we get a seven-dimensional invariant subspace of the trivector fields on the quartic. Now what we're after is a 10-dimensional space, but in fact, if you look at the exact sequence here, and well, so here, what I'm saying, I'm suggesting that this H1 with the two forms has dimension G. So I mean, for a smooth moduli space, this is true. It's true in general that this particular Betti number, if you like, or Hodge number, is the genus. And in this case, of course, the quartic is non-singular. I mean, it's singular. So, but on the other hand, there are very concrete ways of constructing an extension which gives us this class. So I think it's perfect. It's okay to believe that that's three-dimensional, which suggests that actually the invariant subspace inside here is of the right dimension, 7 plus 3, 10, is equal to 10. So this is kind of pointing to the feature that maybe invariance is something which picks out these polyvector fields that actually commute. But so far we're just looking at, we know that there exists, these things exist. We know, we do know from what I proved in the paper that beyond a certain genus, maybe genus 4, that we certainly have injectivity from the dual space of cubic differentials. And so we know these exist, but that they're invariant. but here we can detect some of them. Okay, so I should say this. So forget it. I mean, I'm just repeating things there, but the point is this: how do you get a cubic, I mean, a trivector field out of something in this vector space here? So it's basically this. If you look at, so that's just flat. If you look at, if you like, a 4-vector, flat, trivial 4-vector in 8 dimensions, and that defines something in by projection there. It defines something in the 4th exterior power twisted with -4. If you restrict to the quartic itself, then the derivative of this quartic equation at q equals 0 is a section of the cotangent bundle twisted with O4. If you take, if you like, the interior product with that, that's the way it gives you these trivector fields. And what I'm pointing out here is that you do the calculation. If you look at the bracket of these, so these are not invariant under that group. If you look at that bracket, it's non-zero. So it's just to say that there are all sorts of trivector fields on this quartic which don't commute. And it seems to be the invariant ones which do commute. Okay, there's one last example here. Genus 2, rank 3. So now we know that the moduli space is a double covering of P8 branched over a sextic hypersurface. And here, so here what you can argue is this. If you take the direct image of the structure sheaf, then because it's branched over a sextic, this is OP8 plus OP8 twisted in -3. And so if I have a local holomorphic 3 form on P8, I can pull it back and evaluate on this, then push it forward. That will give me a section of this. I mean, it will give me something down here, which was evaluated on that local holomorphic 3 form. In other words, there is a map from, just think of it as a push-down map, if you like, from trivector fields on here to sections of this holomorphic bundle. And again, you can do the same sort of thing and work out projective space, what this is, then look at the invariance under this Heisenberg group. And what you find is that you get a 4-dimensional space, which again, the curve is a genus 2. So the anti-invariant part of the H1 is 4-dimensional. So to me, this is evidence of a conjecture even, that maybe if we understood these polyvector fields on these moduli spaces, then the invariance under this Heisenberg group, or should actually determine this commuting subfamily. Okay, so but on the other hand, what I've told you is that the integrability, the fact that these things commute according to the Schouten bracket, comes from an infinite dimensional argument, an argument which says, okay, we have this infinite dimensional affine space. These things have constant coefficients, if you like, and therefore they commute. So I thought I would look at a particular case where you can calculate or try and calculate this commuting, if you like, this Gersten-Haber algebra type of commuting exactly. And so I want to look at the intersection of quadrics. So now, in order to prove that something commutes, I have to go beyond the 3-dimensional version. So, but what we know, thanks to a recent paper of, what we know is that from the work of Ramanujan, that if we take an intersection of quadrics, an odd-dimensional intersection of quadrics, then it's, and you can understand this as the moduli space of semi-stable spin C, I think, 2G bundles, twisted spin 2G bundles on the hyperelliptic curve of genus G, which are invariant by the hyperelliptic involution. Now, the Higgs fields are in the adjoint representation, so it's enough to consider SO2G bundles. And the invariance means, according to a paper of Usha-Boss there, that they're equivalent to degenerate orthogonal bundles on P1. So when it comes to looking at Higgs fields, we're going to look at objects on P1. And when it comes to cubic differentials, in this case, a cubic differential on a hyperelliptic curve built up out of a pair of polynomials in one variable, and we're looking at the ones that come from just Z here. And this, so thanks to this paper and an earlier paper of Hering and Razan and Boville and others, this is a way in which we can write the Higgs field as a quasi-parabolic Higgs field on P1. So this is the Higgs field which represents this, this integrable system. So what we've got to do is to work out the trace of phi1 bracket phi2, phi3, and see what that gives us. So in the way it's written here, and this is, in a way, this is one of the nice things about trying to write down moduli space of Higgs bundles, is that we don't necessarily have to have parameters for the base and the cotangent bundle or parameters in the fibers. Sometimes they're kind of mixed up. And so in this case, if you think of it as a parabolic structure, then the parabolic structure at each of these points mu I is basically given by this Ci, if you like, the ratio of this coordinate yi with xi. So then you can say that at a point, so that the cotangent vectors are spanned by, so if you like, if we're fixing a point on the moduli space of parabolic bundles, that's fixing these CIs, and then the cotangent space consists of is spanned by all of these terms here. And so when you work out this expression here, you get this. So effectively, it comes down to this object here, and the polyvector fields look like this. So you can think of it, so the xij's, as I said before, you can think of them as, if you think of the cotangent bundle of a quadric as being a cojoint orbit, and these are just coordinates in the Lie algebra, or you could think of these as being vector fields on one of the quadrics, and it happens that this is actually tangential to the intersection of quadrics. When you take the interior product with the equation, with the derivative of the equation of the second quadric, and this vanishes. So this is defining us a trivector field on this intersection of quadrics. But we can do calculations on the quadric itself. So it has a certain shape, which is kind of familiar. But anyway, so I want to try and show you now why these commute by doing an explicit calculation. To give you some confidence that instead of picking out these trivector fields as being invariant under the involution and relying on a general argument, just to convince you that, this picture works. So the thing to compare to is to the Knižník-Zamolodchikov equation. So this is, if you like, the projectively flat connection for, well, if you put the right omega ij in. But more generally, if you consider this expression, think of omega ij as operators of some type, then if you want these ai and aj expressed in this form to commute for all mu I, then what you need is that they should commute. So we've got these two integers, two indices, I and j. First of all, you want them to commute. The omega ij's have to commute if they have distinct indices here, omega ij, omega kl. And when there's one in common, you want this condition to hold. So I think this is called the Drinfeld-Kono relations. So there's a kind of an analog of this with three indices. And so I don't know whether this appears in the literature, perhaps someone can tell me. But now we have omega ijk. So in that case, omega ij was symmetric. In this case, omega ijk is skew symmetric. And you want the condition on these that the rho i's commute according to this bracket that we're looking at. So if you look at it, you see that first of all, they have to commute when all the indices are distinct. They also have to commute when they have two indices in common. When they have just one index in common, they have to satisfy this relation. So you can see there's a symmetry in this. We've got 1, 2, 3, 1, 2, 3, and then 4, 5, 4, 5, 4, 5. So this relationship and the similar ones, this has to hold if and only if we're going to get these rho i's to commute using the bracket operation. So, well, in our example, we've got this wedge product of elements in the Lie algebra of SON. And so when they have distinct indices, that means that when you have ij, like 1, 2, 3, and 4, 5, 6, then these are actually, they lie in two three-dimensional subalgebras, two SO3s for two orthogonal three-dimensional subspaces. So obviously, the vectors commute, and therefore the combinations have to commute. If you want to calculate the next one, when there are two in common, then, well, you can do a computation. There are only 4 indices here. You can do a computation in SO4. And then the remaining one is this. Well, you can prove this by taking the bi-invariant 3 form on the Lie algebra of SO5 or SON in general and restrict it. And then you express that in terms of these, if you like, monomial type terms. And you'll see that everything vanishes. If you fix omega 1, 2, 3, then the other criteria show that everything vanishes except this. But we know that the bi-invariant 3 form has to commute with everything. And so this is satisfied. So that's maybe a kind of complicated argument, but that's the way it works. As a note, actually, as a side, maybe some of you are interested in these things. So for genus greater than 4, if we look at the usual moduli space of stable bundles, I proved in that paper that there are no holomorphic sections of the second exterior power of the tangent bundle. But in fact, for an intersection of quadrics, there's a dimension, n+3/4. And if you choose 4 things out of the n+3 coordinates of the vector space in which these lie, then you find that this is an expression for them. But you can remark that, so sigma is they're not gamma invariant. So gamma in this case consists of changing the coordinates by ±1 in pairs. But these are not gamma invariant. So although this intersection of quadrics in higher dimensions has these bivector fields, they're not gamma invariant. And nevertheless, they're quite interesting because if you want to look at Poisson structures, so they do exist. So in 3 dimensions, some of these are actually integrable as Poisson structures. Poisson means that they commute with themselves. So bivector fields commute with themselves. But I should say that maybe that I got into this because I gave a talk a few years ago where I claimed on the basis of the back of the envelope calculation that the intersection of 2 quadrics didn't have any bivector fields. And then Peter Bellmans wrote me recently an email saying that this was wrong, that he had a student who'd used a computer to calculate all of these, and that he got a string of numbers, which they put into the online catalog of sequences, which identified it with the n+3/4. So I was kind of intrigued by this, and I thought, well, how on earth are we going to get these bivector fields by choosing 4 things out of n+3? And that means choosing actually a 4-dimensional space with an orthogonal action on it, SO4. So it took me back to actually, 4-dimensional geometry. So if you think of the Lie algebra of SO4 as being wedge 2 of R4, then you decompose that into self-dual and anti-self-dual two forms. And then when you do differential geometry in 4 dimensions using the notion of self-duality, you know that the trace-free symmetric tensors are the tensor product of self-dual two forms and anti-self-dual two forms. If you're a relativist, you'd say, well, that's the energy momentum tensor for the Maxwell field. But the diagonal, if you take the diagonal matrix and make it trace-free, then and put it into that form, then that's what gives you this expression here. So it was like going back to old times and doing a calculation. So I haven't worked out which ones of these are Poisson structures because that isn't my main. Okay, so I should say that the Bellman's student produced this string of numbers for the ones we are interested in, the trivector fields, but that doesn't fit. You can put that into this catalog and it doesn't recognize it as anything. There's something more going on there. Okay, so that's giving you, what is it doing? It's giving you examples. I've given you an example of why things commute, graded commute according to this bracket. But what is it good for? And I think this means that we have to put it into a bigger framework. And this is the framework. So we can think of this as holomorphic sections of the third exterior power of the tangent model sitting inside the tangential cohomology, so the cohomology of polyvector fields. So we have various operations on this. You have the usual exterior multiplication. So instead of having holomorphic forms, we have holomorphic bivectors. But you also have the bracket. You have the bracket operation, not just on holomorphic sections, but on the cohomology. Of course, it's you have to adjust the signs according to the degrees and so on. But we have bracket structure. It's a Gerstenhaber algebra structure on this cohomology of polyvector fields. And one thing you can do is to do some contractions with the classes in the ordinary Dolbeau cohomology. So these are sort of a couple of obvious contractions which kind of reflect what we've got. So the first, actually, I can give you a proof of this one. But so what I'm saying is that what we know is that the deformations of the curve correspond to deformations of the moduli space of stable bundles. So we have an isomorphism there. Let me use the pointer. We have an isomorphism here. And there's an isomorphism here. The H12 is actually isomorphic to the H0K. The H21 is H. So there is a map there given by contraction. And there's a corresponding map here on the curve. So my guess is that these correspond. I haven't proved that. But what I did look at was this contraction. When you look at the trivector fields here, we can contract with this. And we get something over here. We know that we have a map from this space into the trivector fields. We know that this is an isomorphism. And so there's an obvious map from this to this. We know here we have an isomorphism here. So actually, you can do this sort of thing, but relate to the existence of these trivector fields coming from related to cubic differential. And what else can you do? Well, you can look at the, you can say, well, we have this tangential cohomology. We have this commuting algebra, it acts on it. So we have this nilpotent algebra, which acts on the full cohomology. You can ask, is that a non-trivial action? So, for example, what do we know? Well, we know we have these trivector fields. We know we have this term here, so we could look at the action of this. So the action of this on this by the bracket gives us something in here. So it's if you like, it's the Lie derivative action of T on wedge 3T. So on the other hand, there's an interpretation of that. You can either think of rho acting on this, or you can think of this acting on rho. If you think of it this way around, then you're basically looking at the first obstruction to extending this holomorphic vector in a deformation of the complex structure. But we know that every deformation of the complex structure, the stable bundle moduli space goes into a stable moduli space, and so there's one of these for each complex structure on C. So you can expect that class actually vanishes. So the upshot of this is that there aren't many ways, as far as I can see, of finding classes in this cohomology. So what do we know about the tangential cohomology of the moduli space of stable bundles? Well, first of all, so let me assume I'm looking at the smooth case. First of all, if the first Chern, we know the first Chern class is positive, so the vanishing theorem, Kodaira-Nakano vanishing theorem, tells us that these groups vanish when Q is bigger than P. We know, as I just said, that in rank 2, there's nothing in no holomorphic sections of wedge 2T. So that means in particular that you can't look at non-commutative versions of the moduli space. You can look at non-commutative, possibly, non-commutative intersections of quadrigs. We do know that we have these polyvector fields corresponding, we have quite a lot of them. When the rank of the bundle goes up, we can generate them from all the invariant polynomials, the invariant alternating forms. What else? Well, we know we have this class. We have the deformations, Kodaira-Spencer classes. And we also know that if we go right to the top, then the anti-canonical bundle is some power of the standard line bundle, generating line bundle. So the Verlinde formula tells us we've got a lot of sections of this. But as far as I know, I mean, what else can there be? What else? Well, we can take exterior products. So that's the most obvious thing. We can take exterior products and see what happens. And I say this because actually you can do this kind of picture in the symmetric case. You can look at the cohomology of the bundles, the symmetric powers of the tangent bundle. So you start with the invariant polynomials, the sections of the symmetric powers of T. You have H1 of T, and then you can start multiplying and taking brackets and so forth. But at least I believe if you go to the stack, then you see that actually that generates everything, the whole algebra there. There's a paper of, I forget now, Telemann, Konstantin Telemann, which effectively tells you that at least in rank 2, that the kind of symmetric version of this, replacing these exterior powers by symmetric powers, is generated by basically the holomorphic sections of the symmetric powers and H1 of the tangent sheet. You multiply, and so there's a kind of, in the background, there's a question there. Could that happen in this case? In any case, there's a question of what else can we find inside this cohomology? And there's another reason for doing this. And one is that actually this tangential cohomology is the same as the Hochschild cohomology, or it's isomorphic to, by the Hochschild-Kosten-Rosenberg isomorphism, to the Hochschild homology of this manifold. So the Hochschild cohomology, this we know, it's the ordinary Dolbeault cohomology. The Hochschild homology is this tangential homology. That's true initially just additively, but if you act on, so multiplicatively, it's the same if you compose with this square root of the Todd genus. So this is some polynomial in PP classes in the ordinary in the Dolbeau cohomology, acting on by contraction on the tangential cohomology. So the Hochschild cohomology is, no, I meant homology really, yeah, I didn't know. Hochschild homology is graded in this way, and that what we know is that the Hochschild homology is an invariant of the derived category of a manifold, of a algebraic variety. And so, so maybe we can use this to say something about the geometry or the algebraic properties of this algebra of polyvector fields. And so there's been some significant work in recent years, starting with the work of Narasimhan, on the derived category of moduli space of stable bundles. And so there's, I think it's now finally established by Tevelev, that there's a semi-orthogonal decomposition which has components which involve the derived category of the kth symmetric power of the curve, where k goes from 0 up to g minus 1, where g is the genus of the curve. So I know very little about Hochschild homology or cohomology, but what I do know from semi-orthogonal decomposition is that there are Maya-Vietoris sequences, and in particular, there's a map from, in this case, because this symmetric product is part of this decomposition, there's a map which goes this way. And so let's look at what happens in HH2. And so we know, so for the moduli, so this is where, so we've got, okay, this is what we got. And what we know is that, okay, for the kth symmetric product, this one vanishes. I've said that at least if G is bigger than 4, this vanishes and this vanishes. And well, we know that for both, in fact, both spaces, we know that this corresponds to the deformations of the Kadairos-Spencer classes for the curve, and it's a result of Kempf and Teichmüller, and that this also for the symmetric power, the deformation space is the same as the deformation curve. So it seems very reasonable to say that in this, without quite knowing exactly what this arrow is, that the deformations go to the deformations. So I'm assuming that, and I want to see what we can deduce from that. So, okay, so this is what I've just said, that these spaces are all isomorphic. So I want to look at products. I want to look at this class here, and I want to look at products of this inside this space, and see how they correspond to products in this one. So, okay, so when I look at products, when I look at the multiplicative aspect, then I have to change by the square root of the Todd, but these are PP classes, and now, so I'm looking at products of H1 of T, which sits inside here. So that's it. So you see a P, P, P. So actually, you see this goes into the region where the vanishing theorem holds. So in fact, the action of this Todd genus is, or Todd polynomial is trivial on the powers of H1T, so we can use the usual exterior product. Yeah. So what you can show is that in here, in the cohomology, in the tangential cohomology of the symmetric product, you can get some non-trivial k-fold products for k less than or equal to g minus 1, because that limit holds because that's the limit of the power that appears in the semi-orthogonal decomposition. So at least you can find some non-trivial products in this tangential cohomology. by comparing them with this symmetric product. And I'll make the conjecture that these vanish when k is greater than or equal to g. So we've got h1 of the tangent sheaf. We know that they have to vanish before you get to the top, because by the vanishing theorem itself will tell you that top h of the top to have the HPP when p is actually the top dimension is certainly 0. So there has to be some vanishing before then. But what I claim is that the conjecture is that that should happen at the gth point. So in fact, for when g is equal to 2, we know that in fact, so that we look at the three-dimensional intersection of quadrics, then this whole group is equal to 0. But that's maybe not such a strong statement. So, so actually, you can look at the intersection of two quadrics in more general, an odd dimensional intersection of quadrics, and then there's another semi-orthogonal decomposition, but now it involves only one copy of the curve C. So on the other hand, when you can work out these things using exact sequences from the quadric and the intersection with the quadric, and if you like, when you're looking at, in fact, when you're looking at these exact sequences, then basically, if you're on one quadric, then the kth exterior, this bundle here is a homogeneous bundle, so everything occurs in H0. So when you're looking at the exact sequences, you don't get anything beyond H0 and H1. So this vanishes when p is greater than or equal to 2 for an intersection of quadrics. So that's kind of, when I say that somehow there's only one copy of the curve here, and this vanishes. So we have, the conjecture was that this vanishes when the degree is bigger than the biggest power of the symmetric power here. Then this is kind of consistent, if you like, with this picture. And then you can kind of, then everything degenerates into conjectures. So there's this recent paper by Bellmans, again on the intersection of quadrics. So now he's looking at the linear subspaces in the intersection of quadrics, something which Ramanujan, of course, knows very much about. So he has a conjecture here that for this space here, which is also actually, the conjecture involves all of these spaces, that there should be a semi-orthogonal decomposition with powers of up to I goes to k minus k plus 1, where k is the integer here. So here's another moduli. Here's a moduli space of quasi-parabolic rank 2 bundles on P1, which is for the value of k equals g minus 2. So if that's g minus 2, then g plus 1, then that's kind of consistent with this kind of conjecture. So these are just kind of probings, because as we see, even Bellmans, who's the expert on all this stuff, is only conjecturing here that these very concrete spaces have this property. On the other hand, this is a concrete question, and it's possible that by looking at appropriate exact sequences for Grassmannians and so forth, I mean, understanding the geometry of these spaces, maybe it's possible to prove that actually the tangential cohomology vanishes beyond a certain level directly by calculation. So this is all very conjectural, but what I think it emphasizes is that we know so much about the moduli space of stable bundles. We know the cohomology, we know the relations in the cohomology and so forth. But this is one aspect of it which is really not been studied much at all, and it desperately needs some new information. And anything we learn about this, this tangential cohomology says something about the derived category. So it's, this is an aspect, this is a problem, set of problems, if you like, that I leave perhaps to some of you in the audience. And if you don't like that, maybe you can look at that Lie algebra problem I just told you earlier on. So thank you very much.
Thanks, Nigel, for that very nice lecture. Any questions?
Do you expect any modular interpretation of the FK for other Ks besides this G-2 situation?
Well, I think, yeah, I think there is. Perhaps Ramanujan knows this. I mean, the relationship between these linear subspaces and parabolic and bundles on a genus 2 curve with some involution. So I mean, it's not just this. It's not just the.
Not just that one.
For example, the lines in the intersection of quadrics. Do they have a modular interpretation? No. Okay. I think maybe there is. Yeah. I mean, this is picked out here as something which we're familiar with, which is at least in the parabolic situation. But in any case, they have the same flavor and the same many of the same characteristics, which is why I think one of the reasons why Bellman's is looking at these things.
Thanks.
Other questions?
Of this talk, but I just wanted to ask the conserved quantities of the integrable systems, do they have any significance?
Conserved quantities of, well,
significant.
These are skew symmetric. So these are, you can't evaluate these functions. In fact, one other point of view, which one can take, but which I've never found leading to anywhere, is to say that they give the moduli space of stable bundles the structure of a supermanifold. So that you think of this algebra of this you know, graded commutative algebra as the sheaf of functions in the manifold, and then you can say that you can generate vector fields out of them. I mean, they're not normal vector fields, but they're vector fields in a supermanifold sense. And you can, if you like, you can integrate them because they're even vector fields, even though the functions may be odd, the vector fields that they define are even vector fields, which means you can exponentiate them. So on the other hand, they're kind of nilpotent, so that exponentiation terminates. I can do all that with them, but I've never found that it leads anywhere. You know, I mean, you can ask, for example, the question: can we act on? So we have this, if you like, the quantum line bundle. You know, so we can say, can we act on holomorphic sections of that with these vector fields which come from these functions? And you can. There isn't an obstruction, but acting means going from sections of the line bundle L to sections of line bundle tensored with some power of the exterior of the holomorphic tangent bundle. So it's all set up for a holomorphic super manifold structure, but I don't know what you learn from that. I thought about that for many months, but I gave it up in the end.
Other questions? I wanted to ask one thing. So does the appearance of Hochschild cohomology and homology here suggest that there's a categorical origin to the whole, structure and maybe a more general categorical picture behind?
Well, I'm not the person to ask. I think that's the answer. Yeah, well, maybe. I mean, so I'm originally in a differential geometry, and so when I see like tangential cohomology, I'm happy with that. And then the derived category is giving me some structure, cutting down the object into some pieces, which maybe help me to understand this homology. But anything, okay, and so yeah, well, I mean, one could ask, what do the existence of these polyvector fields, what do they mean in terms of, for example, the semi-orthogonal decomposition? Where do they come? So they lie in HH2. Where do they go to at the next level? When in terms of this semi-orthogonal decomposition, what is the geometrical origin of them? And that might indeed help to understand why they commute rather than doing calculations or coming down from infinite dimensions. That's an aspect which might be valid.
Thanks. Other questions?
The symmetric ones in the screen to make a super integrable system.
Well, it's a point. I mean, you can. No, frankly, no. I mean, of course, yeah, you have maps from tensor products to tensor products. Yeah. No, I didn't. I think one at a time is enough. Not combining the two.
Other questions? Comments?
You were talking about quantization of the integrable system in the last lecture.
Yeah.
It seems to me that the odd integrable system, I mean, one could possibly try to apply PV quantization on it because you have an odd Poisson structure and possibly an extension of the Gerstenhaber algebra to the BV algebra. So is there a way to relate these two procedures of quantization for your integrable systems?
I don't think so. As I say, that, for example, the quantization in the ordinary. So what I was talking about in the previous lecture was quantizations of the Higgs bundle moduli space rather than quantizations of the stable bundle moduli space. And we know how to do that using these heat equations. So, but yeah, so the situation is a little different here. As I said, that there's everything, there seem to be no obstructions happening here. You can directly produce from these polyvector fields, you can directly produce differential operators on holomorphic sections of that line bundle, which lie in some tensor power of the line bundle with exterior power. You can define those, and you can even show that there are complexes there. Global actions on it. So you get relations between a lot of holomorphic sections of line bundles, this quantum line bundle or whatever, tensored with exterior powers of the tangent bundle. You get lots and lots of sections of those. Whether that counts as any kind of quantization, I'm not sure. But if you think, it's true, if you think of these objects as functions and in the supermanifold sense, then you can act on holomorphic sections of that line bundle with functions in such a way that the commutation properties hold. So that is a kind of quantization, I suppose. But the level doesn't make any difference there, apart from the fact that it gives you a dimension of the vector space.
Other questions? If not, Nigel, I'd like to, on behalf of Oscar and myself and on behalf of ICTS, I'd like to thank you very much for delivering these special lectures and anchoring the entire program. So thanks a lot. We appreciate it very much. Let's thank Nigel again for a wonderful lecture series.